Our next presenter is Shyam Chandra. He's a security system architect from Lattice Semiconductors, and he's very well known in the hardware security industry, and he's had extensive experience in programmable logic devices. Mr. Chandra received his bachelor's from Bangalore University and his master's from the esteemed IIT Madras. So it is my distinct honor to welcome him on. Shyam, it's all up to you.
All right. Hello, everybody. In today's talk, my name is Shyam Chandra. I'm the security system architect. I work for Lattice Semiconductor Corporation. And today's topic is end-to-end supply chain protection with dynamic trust. So in today's presentation, I'll talk about the supply chain attacks on firmware, and then introduce you to the type of attacks. And then afterwards, I'll talk about the NIST standard that provides guidelines for the system builders to build systems that make those systems resilient against attacks in the supply chain. And then afterwards, we'll go look into an implementation case study, show you how exactly you could do that. And then I'll conclude my talk. So here is a block diagram. On the right side, you can see there are processors, FPGAs. And these are all on a circuit board. And when you power the circuit board on, they have to boot from a non-volatile memory. And that's what I call the firmware or configuration bit streams and so on. So these firmware will be usually stored in a non-volatile memory element like a SPI memory, that is a non-volatile flash memory that has got a SPI hardware interface. So a CPU would boot the firmware, then after booting that, it'll load an operating system, and which will then load the applications, and the whole system does what it's supposed to do. This discussion is about attacks on firmware. So let me answer briefly, why do we care about firmware? Firmware is a piece of code that's going to be resident on the board, and that will facilitate loading of operating systems and some basic hardware interfaces. And if there is a compromise, if there is an attack on the firmware, if the firmware gets compromised, like for example, you have a backdoor to your system, it stays persistent. You can change all the operating systems that you want; it will remain persistent. Okay, so I was talking about the firmware, the need for the firmware. So I also talked about the attacks. If this firmware is attacked, a malicious person could install a backdoor, and they can inflict interrupt the system or bring a totally disruptive disruptions to the operation through the while the system is operating. So it's very important that the firmware is kept in its pristine form. It is always there are no modifications to firmware occurs in the system. So then next I'll talk about supply chain. Okay, so why supply chain? So supply chain is basically all these systems are manufactured at a contract manufacturer, for example, and then afterwards it is sent to the end customer, and then at the end customer side there'll be a system integrator. System integrator would then add some additional components to it and make it ready for operations in the system, and the system starts to work in the final in its final location. It gets connected to the internet or to the network and do the thing that it's supposed to do. So these manufacturing, in transit, system integrator, in system updates, and finally retirement. This is what I call a supply chain. So let's look at where are the attacks coming from. Let's say we have a compromised So on the manufacturing the board where it's getting manufactured, usually they load the firmware and FPGA configuration into the SPI memory in the board. So when you power on the next time, it will go boot and load its operating system. So a malicious operator, compromised malicious actor in the manufacturing could actually install a bad firmware into the board. So you can have the backdoor right from the time it leaves the manufacturing floor, or one could actually install it in while the system is in transit. One could open the box and then put the firmware malicious code there. Or you can have a compromised integrator who can actually go install bad code before installing it into the system. The system integrator also could plug in a internal peripheral, maybe a PCIe card that's got a bad code. And then now the system is working in the connected to the network. You could have hackers coming over the attacking from the network. And then if the system is working in the when the system is working and it's launched all these applications, and one of the application developers could be compromised, and this application could actually, while the system is performing, can go attack the firmware while the system is operating. Or you can have a compromised external peripheral, like for example, you had a USB key that was infected, could plug into the system. That could launch a code and that could go and attack the firmware. So you see that firmware is it is programmable, so whatever malicious code that you throw in there also remains resident and persistent. So how to avoid this, how to block all these things? For that, we need to have security protocols developed on the board itself so that these things are able to detect such attacks and protect and recover from that. And these protocols also should block attacks that come from that originates within the machine while the system is operating, an operation that masquerades like a regular in-system update. So all these things are the way. I mean, you need to block all these attacks to build a resilient system. And that is our topic of discussion today. NIST standard 801 SP 800-193 standard gave guidelines on how to build resilient systems. That is, systems that are resilient against attacks that you might see in a supply chain. So what this standard NIST 800-193, it is also called Platform Firmware Resiliency, or PFR, is based on 3 fundamental guiding principles. One is you should be able to detect compromised firmware or malicious attack code or unauthorized code modification. If you find an error, then you should be able to recover from it. And then when the system you will replace the malicious code with a known good firmware. And when the system is operating, you want to protect the firmware from attacks that originate within the system. So the detection process, it specifies that you have to cryptographically detect a corrupted platform. So there are many systems that have different ways of detecting things. This specifies, hey, you should use cryptography. And and you should be able to look for these errors when the system is powered on or during after in-system updates. And if you find the error during the operation, and you should immediately replace it, either restoring the corrupted firmware and critical data to its previous value, or initiate a trusted recovery process so you get a brand new code, reflash the whole thing, and things like that. And afterwards, you want to protect the platform, firmware, and critical data from corruption and ensure the authenticity and integrity of firmware updates. You want to make sure that the firmware is good. So who should be doing this job, detection, recovery, and protection? For that, NIST specifies that you should use a root of trust device, that is used for detection, root of trust for recovery, and root of trust for update. So a system will have all these three roots of trust combined into a single device is called a platform root of trust. The NIST also specifies that, hey, the coverage should be comprehensive. That is, this platform root of trust should cover all the firmware and the configuration for FPGA. If you don't, that becomes the weakest link and is susceptible for attacks. So a platform root of trust is outside of your applications, and the mechanisms are independent of the type of system. So you can use the same methodology, same NIST SP 800-193 to protect, to build any system, whether it is networking, servers, industrial systems, whatever you're building, you can make that resilient against attacks in the supply chain. So resilient attacks in manufacturing and while the system is in transit at the system integrator or while during the operations, or any of these places, you want to be able to protect it. So next, I will talk about the implementation case study. This is where I show you how one could typically implement, add the platform firmware resiliency function to their hardware to make their system resilient. So let us start with a CPU that is booting from a SPI memory. This is SPI memory is where you store the firmware. So this is what you have today. So how can you make this? What modifications do you have to implement? So what you do is the CPU is now the connection between the CPU and the SPI memory. You add a switch, a SPI switch. It's a very low cost device. And then you add one backup SPI memory. So this SPI memory can be is added so that just in case you find mistakes, as if the main memory is compromised, you could recover from the backup. And we have a root of trust. This root of trust is going to be this is the platform root of trust that is going to administer the protect, detect, recover functionalities in a system. So let us see how this operates in a system. So here we have a CPU, and we have the SPI memory. We have two SPI memories. There's active and there's backup. And we want to authenticate. We want to make sure that the firmware is good and is not corrupted, and that is done to cryptographically authenticate. We add a digital signature to it, and when we add the digital signature, we will add we'll program the corresponding key into the root of trust. So you see that when you power on the first time, the root of trust turns on, the CPU is off, the switch is off, the root of trust directly goes and starts reading the contents of the SPI memory and checking the signature. This is what we call measurement. So you are measuring the SPI memory contents. And if it finds a SPI memory that is corrupt, it is going to make a hardware adjustment so that CPU will not be allowed to boot through this. It'll boot from the backup memory instead of the main memory. And also, the root of trust logs a fault. And so when the CPU comes up, it can read the fault and know that, hey, there was a security breach that was detected, and it is booting from a backup memory, and it can take appropriate actions afterwards. So remember, so this recovery, this routing of this is done even before the CPU and the switch are even turned on. So now the CPU is turned on. The root of trust can integrate the power sequencing and those, so the whole board comes up. You turn the switch on. Now the CPU starts to boot from the backup memory. It reads the log. It knows that it's faulty. So at the same time, the root of trust starts to monitor the transaction that is coming along the SPI bus, and it looks for transactions that are not authentic. For example, if you had a malicious code that came in online, starts to access the firmware, starts to overwrite, it turns the switch off and maintains the SPI memory in its pristine form, just like as it was authenticated. But also, it allows the system, regular in-system updates to go through, and that is communicated through the communication path here. So this is what you have. This is how you implement detect, recover, monitor, and protect functions. That's how you are making your system resilient against attacks. So I know there are lots of new things that you have to add to your system hardware. Lattice provides a solution stack called Sentry, where you have all the IPs needed in a root of trust, the monitoring IP, the streamer IP, the I2C monitors, and so on.
Hi, Shyam. We're
Yes.
Running a little bit long.
Yeah.
Would you be able to wrap it up? Yeah, thank you.
Yeah, I will. So we do have the Propel builder where you can drag and drop all these things into the system, and we provide reference designs, and we demonstrate the whole thing in a hardware evaluation board. And the solutions that are available today, they are usually the TPM-based solution or microcontroller-based solution. TPM is actually a static root of trust. It does not go do all these protect, detect, recover on its own. Microcontroller is somewhat dynamic, but it's not complete. Lattice Sentry provides the full solution. So in summary, the firmware attacks are growing, and supply chains are becoming more and more unpredictable. TPM and MCU-based static solutions are not good enough. So Lattice provides the Sentry. It provides drag and drop IPs on a standard RISC-V processor, and the system it provides you nanosecond level reaction time. So it'll block the IPs blocks the attack as soon as they arrive within nanoseconds. And platform firmware resilience is from the system to the end at the system level. We do have additional protections from the component root of trust device leaving our Lattice site and reaching the manufacturing site through what we call supply guard. That's another topic. So this is what I had. Thank you.
Hi. So good talk. You finished strong. So I have a few questions that are starting to come in, and the first one is from the audience, and they're wondering, how do you guarantee the security of the root of trust?
Very good question. So the root of trust, the device that we have is MachXO3D. I didn't talk about it. I showed you Lattice's platform root of trust. This device also follows the same NIST level standard, that it protects itself, it detects itself, it recovers itself. So this is a container where you put in all your logic, and it holds it in a steel ball. And it's not possible for you to break into it through normal means. You can you get all the way you can still update, but still everything is detected. And this is what we call MachXO3D device, and that's the platform root of trust.
So my next question is, you're talking about how the root of trust monitors from different interfaces to protect against malicious attacks. So do you guys monitor all the interfaces? Are there interfaces that you guys haven't built this for yet? For example, like I know CXL is down the road. Are you guys going to build another generation for that interface? Can you discuss a little more about that?
Yeah, so this device that we have designed is actually for platform, firmware, and I2C buses. So our implementation is totally for these two functions. The CXL, we're doing the protection in the PCIe. We are looking at it. So for now, it's SPI memories and I2C buses.
Okay.
Yeah.
So the next question I had was, the memory has to pass through the root of trust, and then it makes it back to the CPU. Do you notice are there any noticeable, I guess, performance differences because you have to now create that additional waypoint for the data to pass through the CPU? Or is it
So
continue?
the data does not go through the root of trust. The CPU is going to go boot directly from the SPI memory. So the SPI switch is a quick switch, and it introduces something like 500 picosecond delay. So there is absolutely no noticeable degradation in performance. There is some small little amount of time, like 1 or 2 or 3 seconds, depending on the firmware size. Like a 32 megabytes might see a delay of 3 seconds in boot time. So it's not much, you just power on, 3 seconds just goes on. And so there's no wait, for example, or to turn things on.
So this is kind of a general security question. So what is your opinion on a centralized approach for security versus a decentralized approach? Where some people argue that with the decentralized approach, if one device is attacked, then you might be able to protect the others. So you spread your security solution across the entire network and each node.
So the answer is not one. It's not left or right. The thing is, as long as we provide a standard root of trust, there is a definite portion of security that you can really trust. That's the root of trust. From that, you can build different chains of trust and extend the levels of security depending on the application. It is not one block that's going to go manage everything. That's not possible. So you have to build the chain of trust in your entire platform, and then use the chains of trust appropriately. So security is like an application. You have a firmware, and then you have a operating system, and then the applications. You have to build it in layers. Similarly, security is also built in layers. You must start from somewhere. That starting from somewhere is best done from one place where you have full control, and it is auditable. That's what we call a trusted computing base, or TCB.
So you discuss how this root of trust validates firmware. And I don't know if, I guess you answered this and I just misunderstood, but how specifically is it validating the firmware?
So I showed briefly, so when you have a firmware, the manufacturer of the original equipment manufacturer, OEMs, they say, okay, this is the firmware that we developed, and I'm going to sign this. So basically what they do is they measure the firmware, calculate a hash, like a SHA-256 value, and encrypt that hash with a private key. And then generate a signature. I mean, I'm just giving you a 10,000 level view.
Yeah.
So this signature now, and then they put the private key's counterpart, the public key, into the Mark XO3D device, the platform root of trust. So the platform root of trust also does the hash of the firmware, and then reads the signature, and then it authenticates the signature using the public key. So using public key, you can only check the signature. You cannot create it. You need a private key. So private key, you will have to have it in a HSM that is stored somewhere else, that is encapsulated. It never leaves the system. The customer always keeps a private key. He just gives the public key, puts it in the root of trust. So if anybody gets hold of public key, no harm done. You can only check. You can't create.
So who's in charge? Is it Lattice, or is it the vendors themselves who use your product to actually load in the firmware and make sure everything is up to snuff?
It's always the vendor.
It's a, okay.
Lattice provides mechanisms to put the key in a reliable way. The root of trust has to be root of trust. You should be able to trust it. So you should be able to program these keys into the device on a standard manufacturing. You don't have to have guns, guards, and gates to program this device, right? So malicious operators are there everywhere. So Lattice provides, that's what I briefly touched upon, a supply guard by which you can program, the vendor can actually program his key into the device in a securely without having to resort to guns, guards, and gates.
Makes sense to me. Okay. So we're at our time for this talk. Thank you for coming on.